So it's a great pleasure to be here with you, and thank you very much for the opportunity to discuss with you the ongoing project that we are working on with the support of the data utilization program on the validation of the seismic design provisions for diaphragms and the assessment of higher mode responses. The goal of this presentation is to disseminate our research objective to a broad audience with diverse backgrounds, discuss why our research matters, demonstrate how are we using the strong motion data and metadata, and explain how our research relates to and benefits the practice of structural engineering. The main question we are trying to answer is, can we utilize strong motion data recorded from actively monitored buildings to validate the design provisions for floor diaphragms per ASC 7? And before I go there, I want to explain why are we trying to answer this question. And if we go back in time, we can basically retrieve information about the thousands of fatalities and the large number of total damage occurred during past earthquakes. So it's our responsibility as structural engineers to ensure that our design codes can make our public feel safer. Now, if I try to become a little bit more specific with respect to what our project aims to do, we can go back to the 1994 Northridge earthquake and recall the collapses in precast concrete structures and tilt-up wall buildings. And these are special structures, but looking into 2010-2011 Christchurch earthquake, we can see reported excessive damage and even collapse due to the poor integrity of the seismic load path. And this is directly related with the transfer of forces from floor diaphragms into the vertical elements of seismic force-resisting systems. And this is something that research and practice have been acknowledging and are trying to improve our understanding. It's not only about this excessive damage and collapse, it's also about damage that can basically result into a very long process of recovering after an earthquake. And here are some additional examples where we have basically damage reported during earthquake in this transition or connection between the floor diaphragms and seismic force-resisting system members. Now, I want to take some time to describe some of the key concepts that are essential for our project since we are aiming to disseminate our research to a broad audience. And here, I hope you can see my cursor. When we have an earthquake, we have a strong motion that excites the base of a building, and this acceleration from the base propagates through the structure. So we have floor accelerations that excite the seismic mass located at these floors, and the seismic mass times the acceleration induces seismic inertia forces. These forces have to travel from the floor diaphragms, and I call the floor diaphragms because they essentially enforce all the vertical elements of the seismic force-resisting system to move together, which is what we call kinematic compatibility. So all this inertia force have to flow from the floor diaphragms into the vertical elements of the seismic force-resisting system. And this happens through connections in buildings, and here is an example of a reinforced concrete building where you can see this large diameter rebar, where it is responsible for collecting the inertia forces and transfer them into the wall. So once you transfer them into a wall, this force will flow down to the foundation, where we structural engineers design intentionally to have damage at this base for this particular building type in order to control the seismic response of this building during a design level earthquake. However, what happens is we have damage in other locations distributed over the height of the building that we don't design for. One of these locations is the connection between the floor diaphragms and the vertical elements, and as we shown here as a zoom in, and this is primarily due to kinematic compatibility between these two components. And when I say kinematic compatibility, I try to find something that could help us understand further, and I hope you can see my screen. Okay, so well, this is a video that doesn't want to play for some reason. I'll skip. So this is a test conducted by Professor Sritharan at Iowa State that was showing the effect of kinematic compatibility, but unfortunately my PowerPoint does not respond. And the other issue that we face in this type of buildings is the effect of higher mode responses, which may result into high shear forces distributed over the height of the building, and also damage in the non-structural components. And when I say higher mode responses, here typically I use actually the data from the California Strong Motion Instrumentation data program in my classes, but now I'm very happy to use some of the topics I discuss in my classes for this seminar. And here I'll show a little building model that will basically help us understand what are higher mode responses. So this model is subjected to an arbitrary ground excitation, we call it band-limited white noise, and we have this arbitrary motion. But this motion for a linear elastic system can be decomposed into different contributions of modal responses, as we call them. And this is the first mode shape. It's a very particular shape of response where all these floors or degrees of freedom that contribute to the seismic response of this building move synchronously with this shape. And this first shape is what we typically in design practice consider as the major mode of participation in the total dynamic response. However, any building will have a second, third, and so on mode shape, and which will contribute into the dynamic response. And still, these shapes, these higher mode shapes, will have a very specific shape, and will have a synchronous motion between the floor diaphragms in this case. So now the effect of these higher mode responses can be seen from another model we are using in my classes, and you can see when we subject this model to a ground excitation, we can see if we plot the acceleration versus the floor number that we have a high absolute maximum acceleration at the upper floors, which is not the case on the lower floors. So this amplification happens because of typically the contribution of higher mode responses. So how are all these related to our design codes? And if we go to AACE 7, we can see our alternative design provision for diaphragms, where they give us access to the seismic-induced diaphragm design forces called FPX, which are primarily a relationship between the weight, the tributary weight of a floor diaphragm, some acceleration coefficients we compute based on design equations, and the ductility that we expect out of this diaphragm. This is a busy schematic, however, I want you to emphasize on this plot here, where we plot the design acceleration coefficient computing this method proposed by AACE 7, distributed over the height of the building. And you can see this amplification that is captured at the upper level of the structure, which is associated with higher mode responses that we explained earlier. Now, one more thing I wanted to emphasize is the type of parameters that are associated with these computations. For instance, the type of seismic force resisting system for our building is important, the location of the building, the number of stories, and the total height. So all these are parameters that define the dynamic properties of a building. They are considered in this method, and we have to keep them in mind when we select the building stations that are basically monitored through the California Strong Motion Instrumentation program. Now, our main objective, as I said, is to validate these alternative provisions that we just discussed using the data available to us through the Seismic program, and also assess the effect of higher mode responses that we explain what they are. As a secondary objective, we want to populate the additional metadata required to carry all the computations related to our design calculations. Now, we first want to understand what are the metadata available to us apart from the acceleration data, and you can see that among the approximately 450 buildings that are monitored, we have a wealth of data, not consistent in number, but for instance, we can see what type of seismic force resisting system we're working with, or how many stories, and so on. And among these buildings, primarily we have reinforced concrete buildings and steel buildings, and with approximately 2 to 3 stories height, and there are obviously also taller buildings, but are less in number. So considering all these parameters that determine the computations of the diaphragm design forces and also the metadata we have available, we can go and select the building stations that we want to work with. And we look into the construction date of the building station, the number of stories, their location, the risk category, the type of seismic force resisting systems, the number of channels that we can retrieve acceleration data, the spatial distribution of these channels over the height and within a floor plan, the number of earthquakes that have been recorded by a given station, the intensity of these earthquakes, and we also look if these building stations have been analyzed and utilized by other researchers. And then once we use nice tools available online by CSMD, we can retrieve the first information, which means the data and some associated metadata for these building stations. But then we have to go through a time-consuming manual process where we have to extract information or metadata, if you want, related to the computations we have to carry on. And these are related to the type of building or, for instance, the distribution of the seismic weight, the normalized seismic weight in this case, over the height in order to see what's the proportion of, an estimated proportion of this seismic weight over the height, and other parameters associated with the two directions of the orthogonal directions of the building and information that we use to compute our design properties. And then we can develop a workflow in Python, which is an open programming language, in order to carry over all our calculations for all the building stations in the two orthogonal directions and for all the given earthquakes of interest. So we read the metadata available and we start basically processing the information. We can plot this information in terms of velocity, acceleration, displacement, time histories to ensure that we retrieve the correct data in the right form. We compute the big channel accelerations over the height, and we use an estimation of the location of the center of rigidity using the data available to us. And the idea is that we try to minimize the coherence area, which is a measure of correlation between the translational and torsional responses. This is a method developed by Falk and Celebi in 1990, and we just implemented it into our workflow. Now, it is given that there is not a deterministic number for the center of rigidity. There is an evolution for the center of rigidity of any building, depending its actual material properties, the evolution of nonlinearity over time history, and so on. So this is an estimate that helps us next to compute the peak floor displacements, velocities, and accelerations in the two orthogonal horizontal translational directions and decompose the torsional response. And then we can compute spectral accelerations for these instrumented flows based on these decomposed signals. And then, in order to carry design calculations, we need to have an estimate of first mode periods and second and third mode periods. So we used a method proposed by Xiang et al. In 2016 to estimate the first mode period, and a method proposed by Miranda et Angavi in 2005 to estimate the second and third mode period. And having access to this information, then we can go further and carry out design calculations. So we compute the design spectrum and we can retrieve spectral accelerations at given periods associated with the building that we are studying in X or Y horizontal translational direction. And we can compute also the design acceleration coefficients according to ASCE 7 using the alternative design method based on section 1210.3 and also the section 1210.1, which is the commonly used method which traditionally has been in ASCE 7. And then we can compare graphically the peak floor accelerations and also the design acceleration coefficients that we come up for each building station and event. Now there is a problem. The problem is that when we use design equations, we consider that we have a ground motion intensity that is obviously at the design level. However, as you see from this plot, the recorded data we have are mostly from seismic intensities that are lower than the design level. So if you see the y-axis in this plot, we compute the ratio of the spectral pseudo-acceleration at first mode period for a given recorded ground motion over the design spectral acceleration at that first mode period for the building in a direction of interest. So you can see that we have most of this data related to a 50% or less in terms of this ratio. So there is a need to do a fair comparison and assessment of the design methods to modify some of the parameters associated with these computations. And this is basically the effort that we emphasized on this latter stage of our project. And what we are doing is computing seismic performance factors like the seismic response modification factor and overstrength factor, considering an estimate of the intensity that we have actually recorded for a given building. So if we go back to FEMA P6995, it gives a nice definition about the response modification factor and overstrength factor. And you can see all these are obviously computed for a design earthquake ground motion. But as we said, there is an issue with our process. We work with measured ground motion data, which are typically lower than the design earthquake ground motion level. So that means that we get also a lower drift demand, a displacement demand. So we can try to potentially compute a reduction, seismic response modification factor and overstrength factor R and omega respectively for that given seismic intensity that we are working with. And we can do that by assuming linearity of these response quantities, and we can compute essentially an estimate of the R and omega factor at the given intensity level that we have available based on our recordings. So once we have this information, we can go ahead and actually use the ASCE 7 based design equations and compute modified acceleration coefficients considering the seismic intensity that we have observed based on the recorded acceleration data. And so far we are using 4 scaling approaches, and we are expanding on a few more. And what we are doing, for instance, in approach 1, we assume that we have the R and omega factors given per ASCE 7, so we are not modifying them. So the assumption is that we have a design level earthquake and we have the nonlinearity associated for each system with that level of earthquake. And we go ahead and scale the design acceleration coefficient to reflect the seismic intensity, which this scale factor is based on the spectral pseudo acceleration from that recorded ground motion at first mode period for the building of interest, divided by the design spectral pseudo acceleration at the first mode period. So this is obviously inconsistent, but it's a way to systematically basically try to assess each component that is involved with the computation of the design acceleration coefficients. And as you see here in approach 2, we assume that the building is linear elastic. So we use a R factor and omega factor equal to 1, and we do the same scaling process for CPX. Approach 3 assumes that we basically retrieve the information for the roof drift that we recorded from our measured data, and we back calculate an estimate of the reduction factor for that intensity level, and then we use the same scaling method for the value of the design acceleration coefficients to get that modified value of acceleration coefficient. And the fourth approach is use this modified R and omega factors, but go a little bit further and compute CPX, which is the design-based acceleration coefficient, considering information from the spectral acceleration at different periods given the recorded ground motion. So for instance, CS2, which is the acceleration coefficient in our design equations associated with the second and higher mode responses, is computed as the square root of the sum of the squares of the spectral pseudo acceleration at second mode period and the spectral pseudo acceleration at third mode period for that given ground motion we are working with. So having that in mind, we can go ahead and basically assess different metrics. And here is showing only 2 that we have out of a few more that we are working. And the first one is essentially the R magnitude, which compares the average magnitude of the peak floor acceleration that we have recorded with respect to this computed, modified design acceleration coefficient. And the second metric I'll discuss today is a metric that compares the average distribution over the height of the peak floor acceleration and that design coefficient. And this second metric is more on how accurately can we capture the shape rather than the actual magnitude. And if we do this work for 78 combination of building stations and seismic events and use these 4 approaches to compute our modified acceleration coefficients to reflect that intensity level from our retrieved data, and focusing on the magnitude now, how well can these 4 approaches capture the magnitude of peak floor accelerations, we can see that approach 4, which is closer to a more rigorous approach, has the ability to give us good estimates of the magnitude of the peak floor accelerations that we expect at a given intensity level of ground motion. Now, if we move to the basically ability of these methods to capture the variation over the height instead of just the magnitude, we can see that all these 4 methods result into similar results. So that means if you care only about the distribution of the peak floor accelerations over the height rather than the actual magnitude, then any of these approaches could give you a reasonable information. So with that, I would like to conclude and say that the equations that we use to compute the design acceleration coefficients per ASCE 7 according to section 1210.3 can predict reasonably well the magnitude of peak floor accelerations, assuming that we are using our 4th approach, which is essentially integrating information from the ground motion that we recorded at the first, second, and third mode response. Now, the scaling approaches that consider only spectral accelerations of measured motions at first mode period underestimate the peak floor accelerations. If the equations that we compute these design acceleration coefficients now predict reasonably well the distribution of the peak floor accelerations with any approach that we used. Measured data or simulated data at design level earthquake intensity are required in order to fully understand and validate the design provisions. Right? And then additional comparison and error metrics we need to consider in order to assess these design methods, and this is something that we are currently working on this remaining period of our project. And with that, I would like to thank you and acknowledge the support by the California Strong Motion Instrumentation Program and the Chilean National Agency for Research for their support. Thank you.